All right, and so now at this point, for the students who are in pre-calculus, the following detail about polynomials will be explained again when you are really at a formal calculus course. But and so for that reason, I'm about to bring up this following detail, but I'm gonna keep that at the minimal basis right here. Okay. So let's find out what that the detail about the polynomial is. And again, since we're only a pre-calculus, we're only in a pre-calculus level, we're only looking at this detail as a preview of what's going on in calculus later. And so that's the reason why, as I said earlier, I am only gonna keep this in the minimal level, at the minimal basis right there. And then when you go on to your formal calculus course, you will see that idea again, but you're gonna get a real in-depth look at this detail when you're at a formal calculus course right there. Okay, and so when you arrive there at calculus course, you won't be shocked about these nature. So at least because you've had some preview back at this level here, the pre-calculus course. Okay, so it's a detail that's very related to zeros, and I actually brought it up earlier along the work, and now it's time to look into that a little more in a little further detail right here. Okay, so as part of the way how I explained it earlier, and that's not the only way to explain, and that's not the only reason why we're having these natures, but let's say now I'm gonna just bring up a graph of a polynomial on just on scratch. Let's say my polynomial here, somebody is telling me that, hey, we have the graph of a polynomial here, and the graph of this current polynomial has a few zeros, or now we call that horizontal intercepts. Okay, this graph crosses through the horizontal axis at a few places, okay, at a few intercepts. And so now, in some of the earlier examples I was explaining, it's just due to the nature that once we have found all the zeros, which is now put here, once we have found all the zeros, we're gonna put them, and it's the way it is, we're gonna put all of the zeros from the left to the right on the horizontal axis. So our horizontal axis, the x-axis is here, so all the zeros are being placed from the left to the right on this axis right here. And so here's the idea. Now once the graph crosses through one intercept, either going up or going down, it has to turn back to hit the x-axis again. So for example, right here in this improvised picture that I created, the graph first started out rising up, cross through that point right here, and that's why we had that. That's where we had that first horizontal intercept. So in this portion, the graph was rising, and be careful and notice the way how I'm using the term that you have seen in earlier lecture as well. The graph here now for this crossing point, the graph is crossing through the x-axis, the horizontal axis, but in the increasing way, the rising way. But then, in order to achieve and hit back to the next intercept, it makes sense that way that the graph must have had a turning point, a point where it turned down so that it's headed way back down to hit the axis again. And then so now in that way it makes sense now that the graph has to be decreasing or falling. And then once it crossed through that intercept, at some point it has to turn its way again to start rising back to hit at the third axis. I mean at the third intercept. And so that's the nature that I want. That's the detail that now I want to emphasize a little bit. But even though, again, I'm also saying even though we're trying to emphasize here, but I only emphasize enough at a minimal level just to raise your awareness that any polynomial has this nature, and then at your calculus course you are going to look at that at a much more in-depth detail right there. But see, we call these there has to be some kind of point, some kind of place where the graph makes turn. The graph makes turn so that it crosses through at an intercept and it makes turn to hit back and cross through the intercept, to cross through the x-axis again or the horizontal axis again and make turns again. So now we call these points. All right, we call all of these points right here turning points. Okay, so I also refer to these points as peaks. Okay, see, there are so many ways of calling that. So because these are tippy points like that. Now, formally speaking, some people, as far as standard English term, a lot of times people call these the valleys. This is peak and valley, peak and valley, like that. And generally turning points. So in the world of polynomials, we call that turning points. But then this concept is related to the idea we've seen earlier when we were investigating the graphical behaviors of graphs. I mean the graphical behaviors of functions. So there are peaks and there are valleys. But then for my own way of seeing it, I just see that these are just, I all see these as peaks because they are peaking away from where the x-axis is. Okay, they are peaking away, they're going up, and they're peaking up, they're peaking down. Okay, so at least it's a peak in one direction, and here it's a peak in that downward direction. It's a peak in that upward direction. And that's why, to me, when I explain to my students, it seems like I'm going with a little bit out of standard language of the way how the language is used. But then I want to emphasize that it's just about those point that it peaks out. Okay, it peaks out in the upward way and it peaks out in the downward way like that. Okay, but now in the world of polynomials, again, those peaks right there, formally you get the name that we call the turning points. Okay, the turning points. And so here's how it is. Any polynomial has to have a certain number. Any polynomial has to have a certain number of turning points. Because having that turning point as a nature, that's why it can make its way to turn back down or turn back up to cross the horizontal axis again to create more intercepts. And that's the idea right there. Okay, and so the first thing to notice as an observation right here, so allow me to write this in red ink. So any polynomial any polynomial has a certain number of turning points. Okay, has a certain number of turning points. And then, but then I have to open a remark right here. As low as 0 turning point as well. But it's a number of turning points. Okay, so that's the way it is. So now we're gonna get a little further into that, and I just wanna keep that as a minimal right here. We're probably not even gonna have any direct example about this. It's just something that's for you to realize, and then a lot of the better details will be taught at the calculus level right there. Okay, so now all right, so the most important thing about any polynomial is the degree. Okay, it's the degree. So, and we have seen that much earlier in our lecture here, in our lesson here about polynomials. And so now let me bring up a few examples, a few quick examples of polynomials. So how about a polynomial being x minus 1 all squared times x plus 1 times x. It's a polynomial, and this polynomial here is of degree, and up to our experience at this point right here, this is a polynomial of degree 4. Okay, and we have done a good amount of examples throughout so many different polynomials. Let me bring up a few other ones. We've had, how about f of x equals x minus 1 times x minus 4, okay, times x plus 2. Okay, so something like this is a degree 3 polynomial. All right, so and then So now to maximize my board space, allow me to write the following polynomials without indicating the degree. So because here we should be fluent at this point of our learning about the polynomials. We should be fluent with how to identify the degree right out of a given polynomial. So let's look at x minus 2 times x plus 2 times x minus 1 times x minus 3. Okay, and so this is a fourth degree. There's a fourth degree here. There's a third degree here. Okay, so now with these three polynomial, and how about let me change this last one here into g right there. So I have a p of x, I have an f of x, I have a g of x. These are all polynomials. And at this point right here, really into what I'm about to mention, then writing your polynomial in product form, in factor form like this, or writing your polynomial in general form, it shouldn't really matter. But so right now we notice this polynomial here has degree 4, this polynomial here has degree 3, and this one here of course has degree 4, but I'm short of space, so I'm not going to write it out. Okay, so let's use Desmos, our quick, fast graphing utility. Okay, let's use Desmos to quickly look at these and find the number of turning points. Because right now we're in that topic about talking about that details about investigating the turning points on a polynomial. So let's look at the first one here. All right, so for that first one that we're having, so on the left panel right here, I have that function input to my graphing utility right here with Desmos. So x minus 1 all squared times x plus 1 times x. So clearly this is a fourth degree, and this is the graph. And so Desmos is fast enough in terms of generating a graph for us, and it's a pretty precise, nice resolution graph right here. So now as far as the number of turning points, I see one down peak, one bottom peak, I see one high peak, and I see another peak. So right here in what I'm seeing, I count 1, 2, and 3 turning points. All right, so now let's make a note of that. So this polynomial, it has degree 4. And it had 3 turning points. Okay. That one has 3 turning points. And then let's look at another fourth degree polynomial right here. Okay. All right, so now on my graphing screen, allow me sometimes to adjust my function with Desmos right here. So I have x minus 2 times x plus 2. And now I'm going to times x minus 1, and I'm going to multiply with x minus 3. Okay, so now we have a fourth degree polynomial again, and let's look at the graph. All right, so in this way, of course, Desmos is not showing the complete graph right now, but we can zoom it out further, and even with a quite extreme zoom, Desmos is still not able to show the complete point. But now we can predict that there has to be one turning point down here. Okay, and then so there was one turning point. And then there's another one here that makes 2. And then there's another one right here that made 3. So again, I'm going to record that with this polynomial, degree 4, we found 3 turning points. Okay? And that's making it consistent with what I said earlier, even though not too still quite abstract here at this point. That what I said earlier, any polynomial has a certain number of turning points, and as low as 0. Okay, but I still see that as a number of turning points again. Okay, so this statement right here that I made is still not that helpful. So that's why we need to investigate even further. Okay, so now right here in this space of the board, and I led your attention into the fourth degree. So let's look at another fourth degree right here. Okay, so this time how about allow me to hop right into with Desmos first, and I'm going to come up with a different one. All right, so now with a different one in Desmos right here, how about just simply x to the fourth? this is clearly a fourth degree polynomial again. Let's see the graph. Now this time the graph for this fourth degree polynomial has only one turning point. Only one turning point. All right, only one turning point. So, and the graph here was an x to the fourth. That's the polynomial. So now on my board here, allow me to write it down. So this x to the fourth, and now I'm starting to run out of naming. I'm running out of letters to name my polynomial. So just that there is a polynomial without naming it. This one here has it's fourth degree again, but it has only one turning point. All right. And then let's look at another one. Back on my Desmos graphing utility again. All right. So we now have in front of our eyes right here, we now have on right here with Desmos another fourth degree polynomial. And let's look at the graph. Okay. This time the graph has only one turning point because right here indeed it's a flat out right there. So I mentioned it earlier. There are still a lot of details about these turning points that we are not able to, at this point, we're not able to catch all of those details because you need more advanced understanding. Okay, and so now, later on when you will arrive to your calculus course, right there, it will have all of that explanation clearly explained right there. But right now, in how I'm seeing it, this graph here, this polynomial has the graph like this. This is the only turning points we have. Okay, and then right here it's a flat out point, and so all of that details will be explained at a formal calculus course. And that what explains for a flat out point, and this flat out really in a language that I used earlier, this is more like a waterfall situation right here. See, so connecting with what we've learned earlier about the intersection or the horizontal intercept. So at this horizontal intercept we have a waterfall nature because it was odd degree. And then right here we have a turning point, but the turning point here was not at the turning point was not at the intercept. Okay, so right here we have a turning point. So we have a turning point. I mean, we don't have a turning point at the 0 here. Okay, the 0 is right here at x equals 1, but the turning point is somewhere between 1 and that other 0 right there. So there's that turning point, and this is the only turning point right there. All right. And let's record it down again. So that was x minus 1 cubed times x minus 2. Okay. It was fourth degree, and we had one turning point. Okay. And then on Desmos, I've been using factor form most of the time so far. So let's look at another one. Now I'm gonna write a fourth degree polynomial that is in the general form. So how about x to the fourth? And let me hide these interfering graph away. I only want to show the final graph. So x to the fourth minus, how about 5x squared plus 6. All right, so this is a fourth degree polynomial in general form. All right, it's not telling the true story yet. And now as I zoomed out far enough, the true story is being told now. It's being revealed now. Okay, so what's going on here? We have 1, 2, and 3 turning points, right? All right. And then let's record it down. All right, so on this x to the fourth minus 5x squared plus 6, right there, we had 3 turning points. All right, we had 3 turning points. Okay, so now at this point right here, even though we haven't had anyone on the list here, because everything comes out from my own random selection right there, my own creativity. So we just, by chance, we haven't hit into any of those that has only 2 running points. But there should be the 4th degree polynomial, but with only 2 turning points existing out there. Okay, so now here's how I'm seeing it. Most of the time we have 3 turning points, and then there are some of those 1 turning points among the 4th degree polynomials. See, 4th degree polynomial, 4th degree polynomial. So most of the time we've had 3 turning points, and then there were a few times we had 1 turning point. So now, as a general conclusion, as a general observation, I can see that. So we're just writing down as the observations right here. So for degree 4, we found at most 3. It's degree 4, but I found for at most 3 turning points. I found at most 3 turning points like that. Okay, now think about the way how you draw it. Think about the way how you draw it. Okay, so just now degree 4 is an even degree. 2 ends have to rise in the same direction, either both rising or both ending, falling down right there. Okay, and now let's purposely create the easy case where it's crossing with the x-axis, because it will make it clear. So in order to for being a degree 4, that means, see, I already overdrew. Okay, so being a 4th degree has to be something like this. 2 ends pointing in the same direction. Okay, and it has to have, if there are intercepts, then there has to be at most there has to be at most 4 intercepts. And so in that way, if we draw a line through right there, like think of that as a horizontal axis, or you can think of that as one horizontal line right here, then the way how a polynomial 4th degree is, it can be at most 1, 2, or 3 turning points, but that's about the most it can get. That's about the most it can get. So degree 4 right here, it can only have at most 3 turning points. All right. So, and now in another situation of the graph, a 4th degree polynomial, you can think of something like this. See, one peak is lower than another peak right there. All right, so it still can have, see, same direction of the 2 ends where it's going, but 1, 2, and 3 turning points like that. So something like this is definitely, the degree 4 like that. Okay, so at the bottom line, when it's a degree 4 right now, what we have investigated, at most 3 turning points can be found. It could be less. That's why I'm saying at most 3 turning points can be found. Okay, so let's look at those degree 3. On the board I had earlier, we had this. Okay, this polynomial over here. So let me now erase all of these, and I'm going to rewrite this particular polynomial higher on the board. So the one we're looking at now is x minus 1 times x minus 4 times x plus 2. Clearly it's degree 3. Right, it's polynomial p of x. So now on my graphing utility with decimals right here, let's type it in. In factor form, x minus 1, we're looking at x minus 4 and x plus 2. Okay, so now we are ready to pull up the actual graph. All right, so this time for this 3rd degree now, the end behaviors matches perfectly with that property we've learned about end behaviors for a 3rd degree, for a degree 3 polynomial. So the 2 ends go in opposite direction. So now in that way, now in the middle body of that, right, now I see, for this particular graph here, I see 2 turning points. All right, I see 2 turning points. All right, so let's just record it down. And right now I'm focusing on those polynomials having degree 3 like that. So this particular one here has 2 turning points. Okay, and allow me to write that in shorthand writing, 2 turn points like that. Okay, let's write down another one. Let's look at another one. All right, so how about P of x equals, so now we're looking at x squared times x minus 2, for example. X squared times x minus 2. All right, it's a third degree or degree 3. Let's find out, let's quickly pull up the graph using a fast graphing utility. Okay, and then try to investigate the number of turning points here in this particular one. All right, and again on decimals here, I'm going to type in x squared, okay, and then times x minus 2, and I'm going to delete out everything here. Okay, so x squared times x minus 2, and here's our graph again. All right, so again, this is another graph of a polynomial where it has 2 turning points, 1 and 2. And the turning point here happens together with that 0. So now, it's not a hard rule. There's never been a hard rule about a turning point has to happen at a 0. But then you have seen before, some zeros happen to be a turning point. And so in this one right here, the explanation here came out because we have a 0 at even multiplicity, so the graph hits the x-axis or the horizontal axis and turn away. So that's why we had a turning point there at a 0. Okay, so things are still consistent with what we have learned earlier, but then in the end, just simply as counting the number of turning points, this graph has 2 turning points. So this third degree polynomial has 2 turning points. 2 turning points. All right, and again, just we keep seeing more often and more often those degree 3 polynomial with 2 turning points. All right, and now on decimals, let's just look at x cubed. It is a third degree polynomial, okay, and this is among our toolkit's function. All right. And so now for this graph right here, it's simply just a waterfall structure over here, and it has a flat point. So this point here is not exactly a turning point in the sense that it's turning from going up to going down or from going down to going up. So in this way, for now, we can conclude that this x cubed right here, okay, just the p of x equals x cubed. As far as the number of turning points, this one has no turning points. Okay. All right, so it has, for the third degree, for degree 3 right there, we had, for degree 3, okay, we have at most, okay, because we've seen some polynomial, and we have seen some polynomial having 2 turning points or no turning points. So in the end, it's still at most. Conclusion here is among the third degree polynomials, so at most 2 turning points is what we found. We cannot have any fourth turning points. I mean, we cannot have any third turning points for third degree, because think about the graph in the way how we're drawing. Okay, so it has to go up and go down. If we want to make the third turning point, after 2 turning points being the most, if we want to make the third one, that means our graph has to bend down. But bending down means it's going to produce the other end behavior being in the same end behavior with the starting one. Okay, and that's the reason why for degree 3, it has to be at most 2 turning points only. And so, in that same way, when I was explaining earlier about the fourth degree or degree 4 polynomial, we can only have at most 3 turning points, because so now the graph falls down, turn 1 point times, turns 2 times, turns 3 times. If we are having the fourth turning point, because here degree 4 I was explaining earlier, degree 4 I was mentioning earlier that can have only at most 3 turning points. So if we are really trying to make the fourth turning point here on a fourth degree, it cannot be a fourth degree anymore, because it has to turn down, and so now 2n behaviors will not agree with each other. Okay, and so that's another way of seeing why fourth degree can have only at most 3 turning points, and now just third degree polynomial can only have at most 2 turning points. So now, having investigated about 2 different degrees on quite a few polynomials, now we can start drawing out a general conclusion. Okay. All right, so that general conclusion, that general observation is about to be given here. A polynomial, any polynomial of degree n, okay, any polynomial of degree n has at most, okay, n minus 1 turning points. All right, you see, so degree 4 has at degree 4 that we investigated had at most 3 turning points. Okay, degree 3 that we investigated had at most 2 turning points. And then so now think about it, those quadratic as a, so right after making this observation, we can even make it more consistent with what we have seen earlier. Quadratic, those ax squared plus bx plus c right there. Quadratic is always having that graph being in this shape right there, no matter what. But this is the turning point, or that vertex there is the turning point. Turning from downward to upward, turning from upward to downward, turning from decreasing to increasing, turning from increasing to decreasing. Okay, that's the 2 different shapes of the graph for a quadratic. So this is degree 2, and we had, but that's the most right here. That's the most. We have only 1 turning point. Okay, and that's once again consistent with the observation we have made here. Any polynomial of a degree n right here has at most n minus 1 turning point. So degree 2 for a polynomial has at most 1 turning point only. Degree 4 has at most 3 turning points. Degree 3 has at most 2 turning points. So when it says at most, that means some other polynomial of the same degree can be having less. Okay, and that's what it is. Right? All right, so now to get a little more precise right here, at our level, we will not be able to find out, let's say this is a 4th degree polynomial, as a quick picture I'm drawing. Okay, so we will not be able to find out exactly where on the x-axis, where on the horizontal axis that we're going to have the graph turns its direction, turning from the increasing to decreasing, or turning from decreasing to increasing. Those peaks right there at pre-calculus here, we are not able to find these values. But now for calculus, that's hopefully anyone after getting out of pre-calculus here will get into calculus. We'll have detailed explanations about where we can find those x values that cause our graph of a polynomial or any graph to make a turn, turn from increasing down to decreasing, and turning from a decreasing down to back to increasing. Okay, but then now combining with all terms we have learned, again, let me generate a different graph. Okay, x and y axis are here, so a polynomial like this. Okay, so now we have 2 turning points here, whatever degree, well, likely, very likely the least here is degree 3 right here. So now with 2 noticed turning points here, then you see in between any two adjacent turning points. So here it's x equals a and x equals b right here. Between any two adjacent, that's what I meant by adjacent, between any two consecutive turning points like that, then it has to be either a decreasing or increasing only. So in this case here, it's decreasing only, okay? Decreasing only. Because if it's decreasing and increasing again, then that means there has to be another turning point. Okay, so between any two consecutive or adjacent, whatever way you want to call it, but once you have listed down, right, once you have spotted all of those turning points right there, then between any two consecutive, okay, any two consecutive the turning points, and I'm talking about on the x-axis here, right, then it's strictly the interval between that, the interval between any two consecutive the turning points must be either decreasing or something like this, okay, turning points from the left to the right, x equals a, x equals b, this is increasing only. There can only be one nature of the function, either falling only or rising only in an interval that's between any two consecutive turning points, okay, or any two adjacent turning points, to be a little more precise. All right, so that's another details we want to learn and we want to know about these the polynomials. But then, like I said, any more details about these turning points I have to wait for calculus. So here, sadly, I have not pointed out any examples because in my teaching philosophy and in my teaching belief right here, then this is only good enough as a preview for you to be aware, for students learning about this, to be aware that polynomials have those fascinating nature right there. And as you arrive at calculus right there, you will learn the solid technique that you will never go wrong. Okay, the solid technique to track down precisely how many turning points will there be in your given polynomial. Because right here, everything we know is a polynomial at degree n has at most n minus 1 turning points, period. That's all we know. And then everything else, if you want to see it, you have to use a graphing utility. But now I'm talking about even without a graphing utility at your calculus course, you will learn that solid technique to just simply look right at a given polynomial and be able to identify, be able to tell how many turning points there will be. Okay, and then where those turning points will happen. Okay. Really, I'm not trying to make a promotion for calculus course or anything like that, but calculus, in my teaching experience, is a place where it brings all of your algebraic details into a final, solid, very clear explanation. Okay, so I really invite any of my students who learn math here, who learn pre-calculus here, to continue advancing into your calculus courses if you have a chance to. Okay, and so now outside of what I talked here about the turning points here, and I also briefly mentioned about there will be ways to calculate where precisely we have these turning points. Now, let me just mention another detail that some textbooks do, some textbooks don't mention about this, and it seems like a larger majority of the textbooks do not mention about this. So, be also aware that outside of see, you have seen that throughout our graphs earlier. You have seen that we have turning points. Turn from going up to going down, and turn from going down to going up. Those are called turning points. But then we also have those among the polynomials. There are times that we have those the waterfall places, like the flat out points right here. Okay, so I'm not going to get into any more details other than just to raise your awareness that sometimes a turning point turns out to be just simply a flat out point right there. So we no longer call these flat out, at least, and I also believe it's still a controversy out there, it's still a debate out there whether we should categorize these flat points, these flat horizontal points, these flat waterfall point as, the same category with the turning points. So when you arrive at calculus, you will learn technique. Your technique there your calculus technique will consider turning points and flat point as one category. But then as far as the name, these are obviously not the turning points yet. Okay, but I just want you to raise your own awareness that, you know, outside of turning points, your graph also has those waterfall points, like right there in your x cubed that you have seen earlier. Your polynomial f of x equals x cubed. It has a waterfall point right at that. Okay, and then we have learned through our discussions on the zeros of any polynomial. When we have a zero polynomial, and when we have a polynomial in factor form, and let's say x minus 5, it's a zero of the polynomial, and x minus 1 is another zero of the polynomial, but here we're looking at the raised to the fifth power, and here's raised to the third power, for example. So that means with a polynomial like this, see, we have one 0 at at x equals 1. We will have another one, another 0, another horizontal intercept at x equals 5. And then in our explanation earlier, the graph must go through, and it's a positive leading coefficient, so the graph has to do something like this. So it has to be a waterfall point in the way how we understood from earlier discussion. Okay, so it has to be a waterfall point, and indeed, I miscalculated myself a little bit, but this is an even degree right here. It's a total of degree 8, and it's positive, so that means the graph has to do the following. It's falling down, okay, from the left to the right, but doing the waterfall nature. It's not just like a straight going through, it's still crossing through, but starting to do a waterfall nature. Okay, and it has to have one turning point. So 8 degree, but we found one turning point, and then the other points we have are like the waterfall point like that. So when it turns its way up and hits this, it's going to have it's going to create another waterfall point, but even more flat out waterfall point. This is a waterfall point, but not as flat out. Okay, it's not as flat out as this waterfall point. All right, and so these are something that we should be aware in our learning about that. So as far as just turning point, these are not really considered. They're not formally considered as turning points. These are waterfall points. But then when you go to your calculus course, there will be some similarity between that we can put them in the same category with the turning points. However, here at our pre-calculus course, I only want to raise your awareness that outside of the turning points, up and down, or down and up right here, we also have those the waterfall points like that. Okay, all right.